So with this problem, the main pieces of info we're given is that there's an initial velocity of 12 meters per second and an angle of 50 degrees. So now for the first question, we want to know how long will it stay in the air, and we assume it strikes the ground at the same height. So that clues us in that there's no displacement. So we'll get into that in a second. So let's kind of draw out the scene so you guys have a picture. So we have a soccer ball. I'm going to draw that out. I'm going to assume it's a soccer ball. I mean, it's getting kicked. I guess it could be a football too if you're kicking a field goal. But let's just assume it's a soccer ball. Looks something like this. I know. Beautiful soccer ball. I should have went to art school or something. I would have made it in with this picture. I bet Ronaldo, Messi, they would love to kick this. But anyways, it's getting kicked at an angle of 50 degrees to the horizontal. So just imagine you're kicking it like you're kind of kicking it up, trying to maybe hit that top post into like on a penalty kick or something for those who follow soccer or football as they call it overseas. So it's something like that. That's what's going on here. And then now we want to know, we want to learn how long this ball will stay in the air. So what we need to do now is, what I like to do for these problems is we want to split up the x and y kinematics. So like what I like to do is I like to draw out the x section. So I'm going to do that, and the y section. So for x, what I like to put is the horizontal velocity, the displacement, and the time. Okay? I don't put acceleration because in these horizontal problems, like for horizontal motion, we assume that there's no horizontal acceleration. Now in real life with things like air drag and stuff like that, yes, there could be some. But in these simple physics problems, we're just going to assume there's no horizontal acceleration because there's no horizontal force being applied to it. Like if I had like a jet engine or something attached to the soccer ball, then yes, there would be acceleration. But there's no jet engine here, so we're good. And then the other variable is the final velocity. Like we're going to put that in the y section, but we don't put that here because, like I said, if there's no acceleration, we're just going to assume a constant horizontal velocity the whole time. Now in real life, the ball is going to slow down as it's in the air, but we try to keep things simple for these problems because they tell us to ignore air drag usually. So then on the y side of things, we're going to have an initial velocity. We're going to write out the 5 kinematic variables, a final velocity, an acceleration, a vertical acceleration, a displacement, we'll call it delta y, and a time, we'll call it delta t. And the key thing with these problems is that the delta t in the x and y sections, they're going to match up. So they're going to be the same on both sides. And if we can find that time for y, we can plug it in for x as well, and then everything else will work out. So now we just have to plug in the givens. So we know the initial velocity, and we can use that to find x and y. So if we use trig, pretty much for all these problems, unless it's like inverted, you can assume that it's going to be the velocity times cosine of the angle to get the x velocity. And then for y, it's just going to be same thing, but it's going to be the sine. And then you would just put this in your calculator to get this number. Final velocity, they don't tell us. For most of these problems, like projectile motion, it's going to be in the air, so gravity is going to be acting on it. So it's going to have a negative 9.8 acceleration. Oh, and let me put the units. So this will be meters per second for velocities. This will be meters per second squared. And then delta y, that's going to be 0 because they tell us that they assume it strikes the ground at the same height it was launched. So the reason it's 0 is because displacement just cares about your final and end point. It doesn't really matter how high or low this ball was to begin with. We know it could be like 100 feet in the air, it could be below sea level. It doesn't matter. It's starting at the same level it left off at, so that means that the displacement is going to be 0 because it only cares about final minus endpoint. So now that we got this, we can use our kinematic equations to figure out the time. Alright, so I went ahead and wrote all the kinematic equations on the screen here. And the way I like to pick the right kinematic equation to use is I look at the 5 variables, I look at the one I'm solving for, which is time, and then I look for the one that is missing. So I want the one that doesn't have the final velocity. That's how I'm going to pick. So this one has final velocity, so that's not the one we're going to use. Same thing here. This one doesn't have final velocity. So this is the equation we want to use, and then we ignore this one. So let's write out that equation. We have delta x, or in this case, we're dealing with y, so we'll use y instead of x, equals vi delta t plus 1/2 a delta t squared. So then now, what I like to do is go ahead and plug everything in. So delta y, we're going to plug in a 0. Vi, let's type that in our calculator right now. 12 sine 50. That's going to be 9.19. So 9.19 delta t plus 1/2 times acceleration, negative 9.8, and then times delta t squared. Okay, so this is a quadratic, but we're lucky because the left side is 0 already. So all we have to do now is just factor out that t on the right side. So we got 0 equals, let's factor out a t, delta t times 9.19, 1/2 times negative 9.8, that is going to be negative 4.9. So let's do that, minus 4.9 delta t. Okay, and yeah, so that's our factored form. So now when we solve this, we get delta t equals 0 on the outside, but that doesn't really, obviously the displacement is 0 at time equals 0, so that's not important. What we need to do is we need to set this inside equal to 0, because if the inside is 0 and we're multiplying, the whole thing will be 0. So let's do that, and then now we solve. So let's subtract the negative 19 over, so 4.9 delta t equals negative 9.19, divide by negative 4.9 on both sides. Let me type that in my calculator. The negatives will cancel, so I'll just type in positive numbers, and then we're left with, I'm going to round to 2 decimal places, 1.88 seconds. So that is our answer to part A. I'll put a little box around that. Okay, so now that we got the time, let's put it in both sides. Remember, time is going to be the same on both sides. Okay, so we got 1.88 seconds for time. So then now to get the x part, all you have to do is just use the really basic, like velocity is distance or displacement over time equation. So when we do that, you're going to get Vx equals delta x over delta t. And if you're a little suspicious if this works, delta x has units of meters, delta t has units of seconds, meters over seconds, velocity. So then now let's solve for delta x. So when we do that, we get delta x equals Vx delta t. Now let's plug in. So Vx, that's going to be 12 cosine 50, which is going to be 7.71. So let me put that in. 7.71. We know delta t is 1.88. And then now we just multiply the two numbers together, which is going to come out to a final answer of 14.49 meters. So that is our displacement, or how far the ball goes. Okay, so for this last part, we just want to find the max height of the ball. And this is a problem that trips a lot of students up, and this is why I cleared out the whole board. So the reason I cleared out the whole board and what I recommend for these is just kind of start anew for the max height, because we're going to treat this a little differently than the other ones. So for the max height, basically just conceptually what's going on, we have our ball, it's going to go up to a certain height and it's going to come back down, right? And basically at this high point, here's the cheat code. There's going to be a horizontal velocity, but there's going to be no vertical velocity. So basically the max height is where the vertical velocity is 0. So knowing that, we can kind of work backwards and rewrite the kinematic equations to account for that. So let's look at our y. We can ignore x. We don't really. We're dealing with height, so that's not really important. So our vertical velocity is 12 times sine 50. Our final is going to be 0. That's the G code. Just put 0 in. Acceleration, still negative 9.8. We're looking for displacement, delta y. And then finally we have time, but we don't really care about that, so we can just ignore that. So now we have our kinematic equations here. I know, I'm sorry, they still got like the x's on them, but we got to use the one that doesn't have time, and it's going to be this one basically. So then with that info in mind, let's just write out that equation. So we have VF squared equals VI squared plus 2a delta x. But in this case, it's just going to be delta y. So then now, let's just plug in our numbers. So VF squared, it's going to be 0. VI squared, that will be 12 sine 50 squared. So let me type that in my calculator. So we got 12 sine 50, and then we're going to square it. And then that's going to come out to 84.5 plus 2 times negative 9.8 times delta y. So what I would do is I would subtract the 84.5 over, so it's going to be negative 84.5 equals, and then I'm going to multiply these together, negative 9.8 times 2, it's going to be negative 19.6 delta y. Divide out the negative 19.6 on both sides, and then you'll be left with, let me type that in, 84.5 divided by 19.6, 4.31 meters. So that is where the ball will reach its maximum height, and then we're done with this problem. Okay, so now we're going to do another problem you might encounter. This is one where, so there's a cannon and it's on top of a cliff. These are common problems where it's like on a hill or a mountain and then it's being launched. So in this case, there's a cannon, it's firing on top of a cliff, directly horizontally. That tells us the angle is going to be 0, basically. Last time the angle was 50 degrees. This time it's just being shot straight out. And I'll draw out what that means. And then the initial velocity was 1,000 meters per second. So it's getting launched pretty fast. So let's kind of draw this out. We got our cliff. Draw that here. We'll draw our cannon. I know, beautiful drawings, guys. Beautiful drawings. And then so it's getting launched out like this, and then it's going to go on a path that looks something like that. These projectile motions questions, they always have like a parabolic path. So it's going to follow a parabola, and then it's going to hit the ground 30 meters below where it launched. So now with that knowledge, we're just going to do the same thing that we did last time. We will make our table. So let's do the x and the y directions. So we have Vx, which in this case, like I said, it's just going to be 1,000 cosine 0. Cosine 0, it's just 1, so it's just going to be 1,000. I can just write that as 1,000. Delta x, that's what we're trying to find, and then delta t, we'll need this to get delta x, just like we did last time. And then let's write out our y's. So Vi is going to be 0 because 1,000 sine 0 is just 0. There's no, it's being launched horizontally. You can just kind of picture that there's no vertical velocity. Our final velocity, we don't know. Acceleration, it's always going to be negative 9.8 in these cases. We're going to have our displacement, which in this case is negative 30 meters. We know this because the cliff is 30 meters tall. It's being launched, and then when it hits the ground, it's going to be 30 meters below where it started. And then same thing, we want to find time in this case. So just like the last problem, we're going to want to use the equation that has time in it and ignores final velocity. So that's going to be delta y equals vi delta t plus 1/2 a delta t squared. And if you're confused how I picked the equation, just refer back to earlier in the video, and I think it's the same process that I did before. But if you have any questions, just leave them in the comments. I'll be happy to answer. And then vi in this case is 0. So that's nice because when we plug this in, we can actually just ignore this part because vi is 0. And then delta y, so let's plug it in now. Negative 30 equals, we ignore that, 1/2 times acceleration, negative 9.8, times delta t squared. Okay, so then let me type that in. So negative 30 equals 1/2 times negative 9.8. That is going to be negative 4.9 delta t squared. And then we divide by negative 4.9 on both sides. So then that'll be, let me type that in. That'll be 6.12 equals delta t squared. Now let's square root both sides. And then we'll be left with delta t equals the square root of 6.12, which is going to be 2.47 seconds. Now, if you're observant, you might notice when we square root like an equation, we have to put like plus or minus technically for the answer to be correct. But in this case, in the context of physics, time is always going to be positive. You can't have negative time, so it's just going to be 2.47 seconds. So that's why, if you're curious. So anyways, we can plug that in now. We can put that in our little chart. And then now, just like we did last time, we want to find how far from the cliff the ball hits the water. So now all we have to do is just find displacement. We know from last time displacement is just going to be Vx, velocity, times time. So then when we plug that in, we're going to have 1,000 times 2.47. And then that means that the ball is going to hit the cannonball 2,470 meters away. And that is our answer. Alright guys, thank you for watching the video. Make sure to smash that like button down below and subscribe. I also run a tutoring company called MVP Learners. If you need more physics help, go to mvplearners.com, link on screen, also in description, and just fill out the little form. You can just click the button that says book a free call, and we'll get back to you and organize some online tutoring. But anyways, thank you guys so much, and I hope you guys all have an awesome day.